we'll start again here. Solar Eclipse 2017. Everything you always wanted to know about eclipses, but were afraid to ask. Hopefully at some point in your education, you learned that the sun is considerably bigger than the moon. But how much bigger? 2 times? 10 times? 50 times? Believe it or not, the sun is approximately 400 times larger than the moon. Here's what the moon and sun would look like if they were placed side by side. Having trouble seeing the moon? Let's zoom in. So if the sun is 400 times bigger than the moon, why do they appear roughly the same size in the sky? That's because the sun is on average about 400 times farther away from the Earth than the moon is. The hypothetical sun in this diagram is only 10 times bigger than this moon, and has been placed 10 times farther away from the Earth, but it illustrates this point. Note how the images of the moon and sun would occupy the same angle in the eye of the viewer on the Earth's surface. That is, they have the same angular diameter, and would therefore appear to be the same size to that viewer. Drawing this figure to actual scale, 400:1, would have made it very hard to see in the confines of this computer screen. So for the rest of this intro, we'll stick with this 10:1 sun to moon scale. By the way, along with the sizes and distances of everything below being adjusted to show up well on the screen, the angular diameter is also quite a bit off. Each angle shown below is about 13 degrees. How big do you think the sun's and moon's actual angular diameter really is? It's only about 0.5 degrees. This surprises most people. Picture the moon, for example, in the sky. How many moons do you think would be needed to be strung together to reach from one horizon to the other? Does it surprise you that the answer is about 360? Anyway, as you can see above, an angle of 0.5 degrees is really small and hard to see. So, for the rest of the show, we'll go back to using the exaggerated 13-degree angle. You probably know that a solar eclipse occurs when the moon passes between the Earth and sun. But why is this such a rare event? And why is it seen in such a limited area on the Earth's surface? For example, the last time a total eclipse occurred in St. Louis was 575 years ago, on July 7th, 1442. Of course, St. Louis didn't exist until 1765, but the inspiring event was probably witnessed back then by a few thousand members of the Illini tribe. To really understand a total eclipse, it's best to focus on the umbra, that's a shadow that the moon casts, and on something called the penumbra. Penumbra means next to the shadow. Imagine if you were at point A, outside the penumbra, looking up. What would you see? You'd see the full sun, and with the sky so bright you probably wouldn't even notice the new moon beneath it. Now imagine you were at point B, barely outside the penumbra. What would you see? Again, you'd still see the full sun, just like on a normal day. And if you were looking up from point C, well inside the penumbra, what would you see? You would see a partial eclipse, the top portion of the sun with a bottom bite blocked out. And what if you were at point D, just barely outside the umbra? What would you see? This time you'd see a 99% eclipse with just a crescent-shaped sliver of the sun visible. Finally, what if you were looking from point E, inside the umbra? What would you see? Now you'd see the total eclipse. But you're probably thinking, so what? So the sun gets blocked out. What's the big deal? For one thing, the sky gets completely dark in the middle of the day. That's weird. And if it's clear, the planets and stars will become visible. Some animals get confused. Birds and dogs start acting funny. But the really special thing is that the blocked out sun doesn't look like this. It looks like this. Most people do not know that our sun has a huge glowing atmosphere around it, known as a corona. It's there all the time, just as the stars and planets are. But when the sun's out, usually the sky is way too bright to ever see it. The corona is only visible during total eclipses, and sometimes faint colors can be seen in it. Faint green, which is caused by the Fe13 positive ion, and reddish hues emitted by helium-1 positive ions. Chemists discovered long ago that the distinct colors of light given off by energized atoms can be used to identify the elements in that material. Here are some examples. In fact, helium was first discovered in 1868 by a scientist looking at the corona of a total eclipse and seeing a specific yellow color that no element at the time was known to give off. The name helium comes from the Greek god of the sun, Helios. Helium was discovered on the sun 27 years before it was found here on Earth. Another special feature of total eclipses occurs just before totality and then again just after. You would think that the crescent shape would appear like this, but depending on the conditions, the crescent shape often looks like this. These little spots of light are known as Bailey's beads because they look like bright beads on a necklace. Can you figure out what causes them? They are caused by the mountains and craters on the moon's surface. Light passes through in some places and gets blocked in others. Also, you may have noticed on a regular non-eclipse day that shadows cast by the sun onto a distant surface can be quite blurry. That's because the sun is not a point source, and light sort of leaks around the edges of objects, like that. During a partial eclipse, especially approaching totality, shadows become much sharper. With so much of the light blocked out, the sun behaves more like a point source, like that. One more special effect that sometimes occurs in the seconds just before and just after a total eclipse is the phenomenon known as shadow bands. Have you ever noticed how stars shimmer in the night sky? That's the result of light being bent, refracted, by interstellar gases in the space between those stars and the Earth. We say that space is a vacuum, but that's not completely true. Some gases do exist out there. If these shimmering stars were close enough and bright enough to cast shadows on the Earth, then those shadows would appear like wavy bands racing and snaking across our planet. Again, because an almost completely eclipsed sun starts to behave like a point source of light, it has sometimes been known to cast such shadow bands on white surfaces. These shadow bands are hard to capture in photographs or videos, but here's one from a 2001 eclipse in South Africa. And here's a video loop that sort of captures the effect. So why are total eclipses so rare? Actually, they're not. On average, they occur somewhere on Earth every 18 months or so. That's about 6 or 7 total eclipses every decade. But these eclipses occur along very narrow strips, several thousand kilometers long, but often only 100 to 300 kilometers, that's about 60 to 180 miles wide. And these narrow strips often fall on oceans where no one sees them. Recall that about 70% of the Earth's surface is covered by water, or on very remote, uninhabited regions of the planet. One fantastic website you'll want to visit is listed there. If you go there, you will see a chart that looks like this. It breaks up each century into 20-year intervals. If you click on one of these intervals, it opens onto a map of the world showing all the solar eclipses that occurred, or will occur, in the future, during that interval. Clicking on 1981 to 2000, for example, the map looks like this. Note that the blue stripes mark the paths of the total eclipses, and the red stripes are annular eclipses, which will be explained shortly. If you count them, you would see that this 20-year period from 1981 to 2000 has 13 total eclipses and 12 annular eclipses. That's pretty typical for a 20-year span, and it's consistent with total eclipses occurring about every 18 months. Annular eclipses also occur about every 18 months. And here's what 2001 to 2020 looks like. Note how similar it is in appearance to the previous 20-year interval. Any 20-year interval you look at will look pretty much like this. This interval has 12 total eclipses and 14 annular eclipses, and one hybrid eclipse, which will also be explained later. And this total eclipse right here is what all the fuss is about. One thing that is rather unique about this eclipse, it cuts across the entire country, but doesn't touch any other country. For this reason, it has been dubbed the All-American Eclipse. One more thing you certainly notice is that the eclipse paths are generally much wider in the polar regions. Can you figure out why that is? It's more or less for the same reason you cast a much longer shadow late in the afternoon than you do in the middle of the day. Consider how narrow the path is when it hits near the equator. As the moon races across the sky, its shadow would leave a rather narrow path. But when the moon's shadow hits the Earth near one of the poles, the path of its shadow would be considerably wider. But also notice that even within those paths that hit near the middle latitudes, that's near the equator, there is still quite a range of widths. Why is that? That has to do with the fact that the moon's orbit around the Earth is not a perfectly circular one. The moon follows a slightly elliptical orbit. At its nearest point, P, called the perigee, it's about 363,000 kilometers from Earth. And at its farthest point, A, called the apogee, it's about 405,000 kilometers away. When the moon is closer to the Earth, the path of its shadow will be wider. Also, the duration of the total eclipse will be longer, sometimes up to 6 or 7 minutes. When the moon is farther away, the shadow's path is narrower, and the duration of totality is shorter, sometimes only a few seconds. But when the moon is even farther away, something very different happens. When the moon is that far away from the Earth, its angular diameter is smaller than that of the sun's. So instead of a total eclipse like this, what occurs is a partial eclipse like this. The moon blocks out all but the outer rim of the sun. These are called annular eclipses. Annular comes from the Latin word annulus, meaning ring. They can be impressive. But since the sun is never completely blocked, the sky never gets dark as night, and so the corona is never visible. By the way, recall the names mentioned earlier for the parts of the shadow, the umbra and the penumbra? This new area that causes an annular eclipse is called the antumbra. Just thought you'd want to know. A close-up of one of the 20-year intervals shows an unusual eclipse that occurred in December of 1908. Recall that blue stripes represent total eclipses and red stripes represent annular ones. But notice how this eclipse changes from annular to total and then back to annular. This is called a hybrid eclipse. A hybrid eclipse occurs when the moon is just at the transition distance between causing an annular eclipse and a total eclipse. And as the moon's shadow passes across the Earth's surface, the curvature of the Earth shortens that distance and causes the eclipse to change from annular to total and then back to annular. Let's watch that again. See how the Earth's surface starts out in the antumbra, causing an annular eclipse? But the Earth's surface rises up to the umbra and causes a total eclipse for a while. And then the Earth's surface falls away and ends up back in the antumbra, returning the eclipse to an annular one. Of course, one of the most impressive things about eclipses is that they are so predictable. Astronomers have, through meticulous research, obtained such precise information about the rotational speed of the Earth, the angle of tilt of the Earth's axis, the duration of the Earth's revolution around the Sun and the Moon's revolution about the Earth, and the angular tilt of the Moon's orbit, that a mathematical model can be used to predict the exact eclipse times way into the future. Though none of you will be around to witness it, perhaps 40 generations from now, your descendants might be around to witness some great eclipses hitting North America in the late 30th century. Look at all those blue bands. Take this one on September 17th, 2992. So if you Google eclipse of 2992, even though it hasn't come about yet, this website comes up. Open up that site and this map shows up. Zoom in on Missouri and see that although it misses St. Louis, it passes right through Kansas City. Zoom in further and then click on any spot and you get the precise start and stop times of the total eclipse to the 10th of a second. For example, this tells us that on September 17th, 2992, at precisely 3:39, 17.5 p.m., that's 3:39, 17.5 seconds, a total eclipse will just be reaching the 50-yard line of Arrowhead Stadium, and it'll last 4 minutes 11.3 seconds. That's pretty impressive. So why every 18 months for total eclipses? The moon orbits the Earth every 27.3 days, but because the Earth has moved a little bit in that time, the moon has to go a little more than once around the Earth for the Earth, moon, and sun to line up. That's why the lunar cycle lasts about 29.5 days. Since 365 divided by 29.5 is around 12, you would expect the moon to pass between the Earth and sun about 12 times a year, or once a month. This view is looking down on the North Pole of the Earth. First, the Earth is rotating on its axis counterclockwise, and the moon is orbiting the Earth counterclockwise, and the Earth orbits the sun also counterclockwise. So watch as this goes around here. These black wedges represent the shadows that would fall across the Earth during eclipses, total, annular, or hybrid. So why do we not get 12 such eclipses each year? We would have about 12 eclipses each year if the moon's orbit around the Earth and the Earth's orbit around the sun both existed in the same plane, like that. But they don't. The moon's orbit is tilted by about 5 degrees. So more often than not, the shadow of the moon misses the Earth. Sometimes it passes over the North Pole. Other times of year it passes under the South Pole. Recall that the Earth makes one complete trip around the sun each year. Only when the Earth, moon, and sun are lined up and the moon is in the same plane as the Earth's orbit can an eclipse occur. That can happen only here and here. These points are referred to as nodes, and as you can see in the diagram below, these nodes occur each time the Earth revolves about halfway around the sun. In other words, about every 6 months. But only about a quarter, that's 26.7%, of these are total eclipses, 33.2% are annular, and 35.3% are partial eclipses. The remaining 4.8% are hybrid eclipses. Just a quick review of these 4 eclipse types. Partial eclipse, when portions of the Earth's surface end up in the penumbra of the moon's shadow. That's 35.3%. Total eclipse, when portions of the Earth's surface end up in the umbra of the moon's shadow, 26.7%. Annular eclipse, when portions of the Earth's surface end up in the antumbra of the moon's shadow, that's 33.2%. And hybrid eclipse, when the Earth's surface starts in the antumbra, but then rises up into the umbra due to the Earth's curvature. Keep in mind that during total eclipses, annular eclipses, and hybrid eclipses, very small portions of the Earth's surface experience the effect, usually less than 0.01%. But during all these eclipses, huge portions, sometimes over 30% of the Earth's surface, experience partial eclipses to varying degrees, depending on how far away the location is from the eclipse path. To dramatize this point, consider the partial eclipse views the rest of North America will be experiencing as the August 21st total eclipse passes over Nashville. So there you see completely blocked out in Nashville, but Canada, the rest of the United States, Mexico, all getting various partial eclipses at that moment. Here's a sort of eclipse calendar that shows all the eclipses that occur worldwide for the next 6 years. Notice how they come in cycles about every 6 months. Here is the All-American eclipse. Here's an annular eclipse that occurred last February in the South Atlantic. In 2018, there will be 3 partial eclipses, but no total or annular eclipses anywhere on Earth. And here is the next total eclipse that will occur on July 2nd, 2019. It'll pass over the South Pacific and remote areas in Chile and Argentina. By the way, all these red ones represent lunar eclipses, partial and total. A lunar eclipse occurs when the Earth casts its shadow on the moon. Lunar eclipses are fairly common. In fact, one occurred about 2 weeks ago, and totality for a lunar eclipse can last well over an hour. But compared to solar eclipses, lunar eclipses are, well, not so amazing. So, back to solar eclipses. One thing that makes total solar eclipses so special is that they are so brief. Even though the shadow may be 100 to 300 kilometers in diameter, it passes by in just a few minutes. This is a result of how fast the moon shadow moves. The August 21st eclipse will travel roughly 16,000 kilometers in a little over 3 hours. That's averaging about 5,000 kilometers per hour, about 3,000 miles per hour. But the shadow is not traveling at a constant speed. At the beginning and end of the path, the shadow is moving at close to 8,000 kilometers per hour. But in the middle, over the central U.S., it's only traveling about 2,400 kilometers per hour. Can you figure out why this happens? The moon travels at a fairly constant speed, so why is the shadow slowing down and then speeding up? Hint, just like the explanation for the hybrid eclipse, the answer lies in the fact that the Earth's surface is curved. The shadow is actually moving at a fairly constant 2,400 kilometers per hour relative to a fixed spot on the Earth's surface. But watch how fast it appears to be moving at the beginning and at the end. Watch this again, focusing just on where the shadow hits the Earth's surface. See how fast the shadow moves at the beginning and end of the path? The shadow's moving at about 2,400 kilometers per hour, and that's pretty much reflected in its speed across the center of its path. But the moon casting the shadow travels around the Earth at a speed of about 3,700 kilometers per hour. How can the moon be moving at 3,700 kilometers per hour, but its shadow appears to be moving at only 2,400? The moon is moving at 3,700 kilometers per hour, and so its shadow must also be moving at 3,700. The Earth, however, is rotating on its axis at a velocity of about 1,300 kilometers per hour in the same direction. Thus, the speed of the shadow relative to the surface of the Earth is 3,700 minus 1,300, or 2,400 kilometers per hour. To better illustrate this, consider the dots below. They represent 800 kilometer segments. Blue dots are fixed points above the Earth, and red dots are points on the Earth's surface. As the black bar, that's the moon shadow, passes by, try counting 1, 2, 3 for each of the blue dots it passes. This would represent the true speed, the 3,700 kilometers per hour of the moon shadow. So ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then try counting for each of the red dots. Let's try that now with this next sweep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See how much slower? This would be the 2,400 kilometer per hour shadow speed that we will be experiencing here in the US. Slower than 3,700, but still very fast. By the way, if the Earth were spinning in the opposite direction, but everything else remained the same in terms of their orbits and rotations, then instead of subtracting these two velocities, we would be adding them. Instead of an apparent shadow speed of 2,400 kilometers per hour, it would be more like 3,700 plus 1,300, 5,000 kilometers per hour. If that were the case, total solar eclipses would last only about half as long as they do. So why are eclipses so dangerous to look at? With 99% of the light being blocked out, shouldn't a partial eclipse be less dangerous to look at than the full sun on a normal day? The truth is, looking directly at the sun on any day is a bad idea. But we and other animals have acquired, through evolution, protective behaviors that help us avoid this risk. Our pupils quickly dilate, that means they get smaller. We squint, and we instinctively turn away from such a bright light source. It's easy to imagine in the evolutionary history animals that did not possess the genetic disposition for these innate reflexes. They would go blind, have trouble finding food, die out, and not pass these genes on to the next generation. It's known as natural selection. But what makes eclipses so dangerous is the fact that they are not as bright as the full sun, and therefore the reflex to squint and turn away does not get triggered. A person can comfortably look at a partial eclipse for a long period of time and not feel any need to look away and not realize they are doing permanent damage to their retina. The light enters the eye, gets focused on the retina in the back of the eye, and burns it. And since the retina has no pain receptors, the damage is done before the person even knows it. Of course, the only way to look directly at the sun for any length of time is through very dark filters. Yeah, there's one in every crowd. By the way, you will want to keep your eclipse glasses on all the way up to the start of the total eclipse. Then you will definitely want to take them off so you can witness the corona and the stars and everything. But then you will want to quickly put them back on before the sun peeks out after the totality is finished. In fact, a lot more damage can be done to the eye immediately after a total eclipse than can be done immediately before it. Can you think of why? Before the total eclipse, the pupil of your eye will look like it normally does during the daytime. But during the eclipse, your eye adjusts to the darkness by dilating the pupil to allow more light in so you can see better. But the dilated pupil will mean your eye is especially vulnerable right after the eclipse passes. So be safe. Sorry, but we're going to end this slideshow on a sad note. Go back to the Apollo lunar missions of the late 60s and early 70s. We all know that those fearless astronauts brought back all kinds of rocks and soil samples from the moon. But can you think of 4 things they left behind on the moon? 1, their footprints. 2, the American flag, of course. 3, a golf ball. And 4, a mirror facing the Earth. That's right, a mirror. And astronomers since then have been bouncing light beams off that mirror and timing how long it takes for the reflected light to return to the Earth. About 2.56 seconds on average. Using that information and the speed of light, 300,000 kilometers per second, they can make very precise measurements of the moon's average distance from the Earth. But here's the sad news. They've discovered that the moon in its orbit is very gradually drifting away from the Earth. It amounts to about 3.8 centimeters per year. That's about 1.5 inches. To put that in perspective, that's about how fast your fingernails grow. What that means is, eventually, over the years, total eclipses will become less and less frequent, and annular eclipses will become more frequent. Here's how things are now. A good mix of total and annular eclipses. But this is how things will be a few billion years from now. See, with the moon so much farther away, no more total eclipses, just annular ones. So appreciate these total eclipses while you can. The end.